Hi, I'm Matthew Cox.
I'm Zach Arnold.
I'm Owen Harshbarger.
And I'm Jackson Jorgensen.
And today we're going to be looking at the physics of a golf ball. The context of our problem: in this scenario, we're given the velocity of a golf ball in the x and y directions, and using the calculations or the calculus for non-constant velocity and acceleration, we need to analyze and represent the position and acceleration equations and graphs of the golf ball, assuming that we're near Earth, that there's an air resistance or drag that's acting on the ball. We are representing the ball immediately after hit, so the initial position should be 0. And we are also using the particle model, which assumes the ball has no rotation. And in the end, we're going to be trying to compare position and acceleration given the velocity function of the ball.
I'll take this part of you.
I got it.
All right, so this is the position function of our graph. So in blue we have y, and in red we have x. So as you can see, both functions start at 0. And as the y function increases, it goes up. The position gets very high, and then goes back down to 0 at point, whatever that point is. Whereas with the x function, it increases and increases, and then it flats out once the y function also hits 0. And so it stays standard at that point because the ball stops moving as soon as it hits the ground. So using some sense making, so if we manipulate b, which is our drag coefficient, we can see that, as b gets smaller, our distance traveled drastically increases because there's less drag on the ball. Whereas if we manipulate stuff like as it gets bigger, the opposite happens, and the ball travels far less distance. If we play with our initial velocity, as that decreases the initial velocity of our x component, our ball travels way less far. And when it goes negative, it just breaks, and it doesn't travel. It travels a negative distance. Yeah.
If our air resistance, goes to 0, we have a special case where our function completely breaks, meaning you can't divide by 0 in either sense here, which means if there's no air resistance, the ball is going to travel infinitely.
Okay, so here we have our velocity graphs. The green line is going to be our velocity, the x component of our velocity. So as we can see, it starts up here at 36 for our initial velocity, which you can find in the equation. And then it's going to slowly fall down until it reaches or approaches 0. So the ball is going to be slowing down to a stop, or infinitely close to a stop. And then the yellow line here is our y component. So we can see that it starts up there at 60, and it will decrease, and it will hit 0 where the peak is of our position function, and then it will go to a negative value as it's falling down, and it will stay there. Do you have any special cases for that one?
So, for the x component of our velocity function, if we decrease the initial velocity, we can see our point here on the velocity graph will continue to decrease to match. While this does affect the intersection on the y-axis, it doesn't affect our final velocity. Similar thing happens with C2. It will decrease, but it won't impact our final stopping point. And then if we were to increase B while keeping everything else constant, it wouldn't affect our x, but our y component in the velocity would begin to increase or decrease, being that if there's more drag on the ball, it won't be able to be in the air. And then for these, if we were to increase gravity, a similar thing happens.
So for both our x direction and our y direction, we see a very similar shape in what's happening with our acceleration components. Both the accelerations are going to be decelerating until they reach this certain point up here, which is when the ball hits the ground, and it will be back to zero. The acceleration graphs are basically showing how it starts at a high initial velocity and it decelerates as the ball gets affected by drag and gravity until it hits the ground and eventually reaches zero.
So for our x component, if we were to decrease the initial velocity of our x component, we'll see that our graph starts to shift as it decreases to the left, which basically shows us that it's decreasing less the function of time, but it doesn't affect the final output, similar to the velocity. And a similar thing happens with C2, the other initial velocity. Our y component will continue to shift to the left, and as we get to the negative, funky things happen. If we were to increase b, both of our lines shift, and eventually would become very homogeneous. And then if we were to have negative drag, it breaks. And same with gravity, it's not affected other than the x component because it relies on it more. Looking back to our activities in class, we completed this marble activity as an in-class activity during lecture. It is a very similar thing where we're using acceleration, velocity, and position functions to predict the different movement of the ball. We have an angle which is very dissimilar to our problem, but at the same time it's similar to our problem. We have the marble's speed and the marble's position, and we can use our equations to calculate the golf ball's position as a function of time, as well as its velocity and its acceleration. Next slide. This problem helps us demonstrate our physics understanding. We have this graph display up here. While it does look like a massive jumble, it allows us to show our position functions, our velocity functions, and our acceleration functions. And we can see how these compare over time. So for our position, we have our y component increase as a function of time and then decrease back to zero, while our x goes like this. Now if we were to analyze the velocity with that, we would see that it's decelerating as we continue, or it's speeding down.
Decelerating.
That's acceleration.
Oh, slowing down.
Slowing down. This problem clearly demonstrates our physics understanding. Up here we have all of our graphs plotted at the same time. We can see in red and blue our position functions, in yellow and green our velocity functions, and in purple and black our acceleration functions. We can then see how each of these are related. As our y increases as a function of time, it will peak at the top and then get back down to zero as the ball rises and falls with time. And our x component will increase as a function of time, meaning that it's traveling further and then it will eventually level off when it's traveled its maximum distance in the x direction. With that, we see that our velocity functions of the x and y components cause the ball to slow down as a function of time. So we see that as y gets higher and higher, it reaches its peak and then it goes negative, meaning that the ball is speeding up as it goes down into the earth. Whereas our x function will just reach a speed of zero, meaning that the ball has stopped in the x direction. And then relating our velocity functions to our acceleration functions, both of them will continue to increase as they have been decelerating, but when they reach zero, our balls have stopped accelerating, meaning they have reached the final position. as a whole, this problem has helped us demonstrate our physics understanding great. It's been a great opportunity to like brush up on our skills, and overall it was a good problem. And it was great to relate it to an in-class activity. Thank you for watching. Any closing comments, anyone? Thank you.
Thanks.